Morning, students. I didn't press, and I didn't unmute my mic. It's unmuted now. Um, Welcome back. This is our second last series of lectures. The last one should be on Monday, and then you don't have to worry about moms anymore. So that's going to be good. However, this chapter is also included in your second test. So ensure that this weekend you start practicing it. I will see you on Friday, so I'll try to bring all your scripts with. When I say try, and I mean all the subjects you've registered for. You guys are free to come collect it. So I'll do that. So I'll see you on Friday, and then on Monday we'll be doing breaks. And that's where we'll conclude. However, I do want to use Monday as well, just as a maybe towards the end of the lecture or session towards the end, maybe tackle one or two always problems to get you guys well acquainted. Is that cool with you guys? Mr. Kiefer will remind me towards the end of that lecture to make sure I do around maybe two voice problems. Is it okay?
Sure. Is that at the end of this lecture?
No, on Monday.
On Monday. Okay.
Oh, it's fine. It's fine. But first weekend, focus on belt drives. So yeah, so belt drives is not a difficult section, just a lot of formulas, and you just need to know where to use what formulas. And I'll try to highlight each and every salient concept of this section. But I promise you, once you know to, it's literally a plug and play kind of thing. But then you of course have to manipulate here and here. So it's a very easy marks to score. I just want to make a note of you. I've said at the final is that you can select either a belt drive question or a brake question. They're both around 15 marks. So if you're good with brakes, you can do brakes. If you're good with belts, you can do belts. And all the rest is compulsory. So I hope that is clear to everyone. Can I get a thumbs up? Are you guys listening? Yeah. And Elisa, you did fairly well in the test. I would just like to ask you, is there any advice for our fellow students in your studying approach? What is your study approach? If you don't mind me asking. For mechanics or machines anyway.
Excuse me, sir? I didn't hear the question.
And Elisa?
Yes, sir. Can you hear me?
Yeah, your mute. Not mute. Your mic's a bit too soft. Your volume very low.
And now?
Still poor.
Okay, should I type?
Yeah, you can type. No, my question was just like, what is your study approach? You usually feel well for the test. So what's your study approach for moms? Just as a guide for some students. So I think the way I lecture is fairly easy. If you can pick up, if you're listening. Are you gonna type that out or don't have to?
Yes, I'm trying to type.
Okay, cool. Okay, guys, let's just start with belt drives. Right. Okay, chapter 7, belt drives. Right, second last chapter. Here we go. So before we start with belt drives, I just want to discuss what mechanical power transmission. Right. So what they say, mechanical power. Oh, is she saying something? Ready now? Yeah, that's the best way. Really go over the slides first and then practice the questions. It's literally that simple. Don't make things too complicated. Yeah. Okay. So mechanical power transmission involves different types of systems to transfer energy from one component to another without changing its nature. That sounds a bit funny. When the motion is coming from a driving mechanical component, it is transferred to another without being changed. There is power transmission, right? In mechanical power transmission system, the moving component transfer energy to the receiving component, right? These components can be by direct contact or can also be transmitted by an intermediate contact, right? So we transmit power, right? So we want to transmit power from one place to another. This is particularly mechanical power. How do we do it, right? Of course, there are ways that you know, and we can use, for instance, positive drives. We talk about shafts is one way to transmit mechanical power. You can use flange couplings, gears, and dog clutches. That's another way. But let's get into this. So, a typical mechanical drive is only bifurcated into two types: the friction type, and then your positive or mesh, right? So your positive types are like it's not also here. It's like your chain drive and gear drive. Shafts are also part of that, and your dog clutches. They're positive. And then your friction type, right? So of course the friction drive is the principle of friction, and what it also means is that when you're talking of positive and friction types are more likely to slip. Essentially, they are belt drives, and then from the friction drives, which very common are your belt drives and your rope drives, right? Okay, and then from your belt drive, it can be further classified into your flat belt, your V belt, and your timing belt. So what we will be exclusively focusing is on your belt drive component, obviously. Gear drives, gears, you start touching on in ones 3, and I'm not sure if we will be looking at all the different kinds of arrangements. So I'm just making aware that this is a form of mechanical power transmission. So this is one form of it, right? This is the, we're looking at the, nearly, you would say that arguably the design and the analysis on how to do this. Okay, so this is the intermediate slide of we'll get back to this. So just showing, you got a typical arrangement, you got a driver pulley, and it houses a shaft, so this of course is a bearing inside. Likewise, with you got the driver pulley and the big pulley. What's the driver and the driven pulley, right? It's just showing the tensions, and of course to drive it, and on the right hand side it's the same arrangement, but of course to turn it we need a motor. Of course, turn the driver pulley, and then what we call the small pulley again. Why small? You know, the driven pulley, the driver, the driven pulley. Right? You'll get back to the terminology again. But the idea is that the motor's transferring power to the small pinions, or arguably pinion, which I'm thinking in terms of gears, and then to the bigger one. Right, so just transmitting power. It's more into okay, so different types of belts. Before we actually get into all the analysis, just things that are important to go over this. You've got your flat belt, you've got a V belt, and you've got your rope belt. So those are the 3 things we're actually looking at today. And they say flat belts are mostly used in factories and workshops. We have moderate amount of power to be transmitted. Moderate from one pulley to another, when 2 pulleys are not more than 8 meters apart. So that's very important. Eh? So if you ever want to transmit power, you just can't use any belt. There are conditions. The V belt is mostly used in factories and workshops, just like the one before, and exactly the same. And they say base, but you use a V belt when 2 pulleys are near to each other. So that's when you prefer to use a V belt compared to a flat belt. Maybe we can find out why. And of course, you've got your circular rope belt, and this is more interesting. And see, the circular rope belt is mostly for factories and workshops. Really, same thing again. We have a great amount of power to be transmitted from one pulley to another, but with the 2 pulleys are more than 8 meters apart. So for your V belts, ideally you want to be pretty close. For your flat belts, you've got in less than 8 meters, and for your circular, more than 8. So if you're on board a ship and you are required to transmit power, or maybe if you're looking at a particular engine, you can actually kind of gauge what kind of, depending on how they're transmitting the power, if it's a belt drive, you know what belt roughly it should be, and there are reasons why. course, you just got a typical pulley range in there. Got a pulley over there on the right hand side. It's like an idler pulley. It's got different grooves. Of course, the grooves is there so that I can grip on the belt. It's just a side picture there. For the materials, this is really just for information's sake. Nothing worth going. It's normally leather, rubber, or canvas, or palata. But the idea is that it's all to do with having a good coefficient of friction. This is just also for more information's sake. I will not ask you what types, but just what type of material. But the idea is where this all ties in is that it's about the coefficient of friction. You want something with a good coefficient, right? Okay, so just users comparing belt drives, the advantage of using belt drives. It's easy to store and remove. I'm sure if you've anyone done a basic service on a car, they have done this. The price of the belt drive is low, that's true, right? Simple in construction, the maintenance cost is low, no additional lubrication required. For instance, if you're using gears, you probably need lubrication. You can transfer power, vertical, horizontal, and inclined to normally on conveyors, that's the idea there. And the power consumption is low. The idea there, what they probably mean the power consumption is low, is that the mass moment of the actual system is low. When we talk about the gear drive, gears have, in particular, even clutches have big mass moment of inertia, so it takes more energy to rotate. Disadvantages of the belt drives. There's power loss due to slip and creep. Very important. I would like you guys to know that. Even though I'm talking too much about creep, they're not used for very short distance. Speed is limited to some extent, and that is very true. It is quieter. I don't know how that's a disadvantage. That's actually what we want. Longer life is not possible. Yeah, charges of braking are more, and it has a limited operating temperature. And if it gets too hot, you know, there could be thermal stress induced within the belt. And they say that the angular velocity ratio is not necessarily constant or equal to the ratio of the pull diameter to the slipping. Now, that's a very, very important concept, guys. I just want to say that again. The angular velocity is not necessarily equal or constant to the ratio of pulley diameters to the slipping. You're going to be doing a calculation where you're going to find out that the belt's going to slip, and then the ratio of velocities in the belt is not equal. I'm sure you guys are aware, knowing that the linear velocity, even though the angular velocity is not constant, depending on the diameter, of course, but the linear velocity itself is not actually constant. So that's because of slip. Cool. Just like comparing to other systems. So the main elements, slip, suitability, space, that's all the particulars. So belt drives have pulleys and belts. Slip may occur. Look at the chain and gear drive. The spousal drive is definitely no slip. Belt drive is good for large distances, but of course depends on which kind of setup you're using. Requires large space. It's so very simple. It's simplest actually. Failure of belts does not occur. Yeah, that's a very important concept with belts. When a belt breaks, it doesn't cause severe damage on whatever machine is transmitting, but with a gear drive, you can sit with several problems. So that's a nice thing of belts. It doesn't affect other components. Life, in comparison to gear, so it's less. It's going to break quicker. Of course, installation cost is less, and it uses for low velocity ratios, right? So fast you want to go, ideally you want to use gears, and that's going to come down to centrifugal force. So when you're spinning something, you're going to get an extra force acting on the system. Just looking at this, they say like flat belts will run at good satisfactory speeds just over 20, and a safe speed around 15 to 70.5 meters per second. So that's just to supplement this for low velocity ratios. Okay. Next, so now we just gonna clarify further what flat belt drives are. So you got an open belt drive, right? So what they're basically showing there is like two shafts, pulley and the belt's rotating. Now, what's just important now as we are here is that if you look at the direction of rotation on, so it's going to be the driven pulley and the driver pulley. So I was right. So I'm just thinking again, the opening and I don't know. So it's rotating clockwise. And if you look at that, you're always going to find out that the bottom side is the tight side, right? And the top side is called the slack side. What it means, the tight side essentially is the tension is more on the tight side compared to the slack side. So that is just now for information sake. But as I of course continue the lecture, it will kind of make sense in a way. So just be aware. So as it's rotating, the direction of rotation, I guess, on the top side will be slack, and the bottom will be tight. So just getting something, yeah. So just to make you aware of that. Okay. So with flat belt drives, you get across the twisted belt drive, and yeah, it's literally showing you there, and it says used for shafts arranged parallel, rotating in opposite directions. Right? Did I digress into this one? Yeah. No. Yeah. So for open belt drive, we normally use shafts arranged parallel, right, and rotating in the same direction. So they rotating in the same direction. Whereas your cross belts, they're rotating in different directions. So you can see pulley A is rotating clockwise, whereas pulley B is rotating anti-clockwise. And then we're going to set up a cross belt drive for whatever that is. So that's also very interesting thing to kind of identify which type of belt you should use. All right, there's also other types of belt drives. Unfortunately for us, we won't be doing any analysis on this. So you got your quarter turn belt drive. Of course, that was more for incline purpose. And we also got a belt drive with a single idler pulley. You might see that. It's not something which I'm always going to bring up. But basically, the angle of the idler over there is going to increase the angle of lap. But we might do an example of that. It's not, I'm not really focused on that. And of course, we've got one of many idler pulleys. It's really sophisticated. Then we got a compound belt drive. We have a driver. There's 3 shafts over there. I'm not particularly sure why one we want to transmit power like that, but okay, it kind of shows you there at the bottom. But it essentially have 2 belt drives parallel to each other. And yeah. All right. We're nearly to the example. So velocity ratio of belts. So this is something familiar with you. What you basically assume that the linear velocity is exactly the same on the drive and the driven pulley. Show you a relationship pi dn or pi dn over 60. The idea is that you make that equal to each other, and then pi will divide out, becomes 1, and then you have some kind of ratio. So without slip, the velocity ratio, the rotational speed of N2 over N1 equals D1 over T2. So you could call D1 the driver and N2 the driven. But now it's important with belt drives, we have to include the thickness of the actual belt, because I mean that adds to the dimension of the actual pulley. Now, this is not always the case. I think I probably have a small example for that somewhere here, but I can't exactly tell you how much percent it is. So I think, to be honest with you, it's arguably negligible, but I might do an example to illustrate, or I'll show you an example just verbally on. But anyway, we do consider that to make the results more accurate. Okay, so we start doing equations now. It's starting to start getting fun. Okay, I just want to get over it before I get to the length, right? So I just want to make you aware of one particular variable, and you would see something's called the angle of lap. What the angle of lap is essentially, it says here, it's the belt makes contact with the pulley over an arc with the pulley circumference. Yes, as you can see in that image on the left. And that's known as the arc of contact. This arc is obtained by an angle. The center of the pulley known as the angle of lap. So that angle over there, basically where the pulley is, I guess, that's around the circumference of the pulley, the belt surrounding the pulley. That is going to be angle of lap. You can see on the right hand figure over there, it's exactly the same. And that's just angle of contact, angle of lap, same thing, just to make you aware of this terminology. So this formulation over here for the length of the belt drive, this is in your formula sheet. For the flat belt drive, that's how you compute the length. Since you're using it's just simple, geometry. You can always have a look at this. So just be aware for your normal flat belt, it's going to be the only difference between the two, the cross and the flat, is that you've got the distance subtracted from each other, whereas the cross belt you're going to have to add. I think I would have liked to go over this, but I think when we do the first example, we can actually unpack that a bit better. They are just models to compute the length of the belt. Okay, yeah, so again, with open and cross belt, there are more formulas. So total the angle of lap and the length. What's important to note here is that we're talking for a while. Let's say in an open belt drive, the diameter of the pulleys are not the same, the angle of contact of the two pulleys are not the same. So that's very important. So what we tend to find is that the angle of contact on the smaller pulley, which is now Peter 2, is less than 180, as compared to larger pulley that's greater than 180. So what's important about that is that slip will occur first on the smaller pulley. And when we're doing our analysis or calculations, we always have to use the angle of lap on the pulley, because slip occurs there first. If slip occurred on the driven pulley, then we don't have the angle of lap. So let's just get more information there. And that's the equation how to use it. It's just basic. We can always unpack it, and we're going to unpack it in the first example. Just making you aware of that. I initially didn't include in the formula sheet, but I did include that in the formula sheet now. And so I'm just making you aware of that. So that'll be negative. So it's theta equals to R cos R1 minus R2 divided by X. X is the total distance between the two shafts. You'll get that. I didn't actually mention the variables, but yeah, it's fine. For cross belt, again, so the cross belt is they're just giving you, again, the same thing, two different directions. And the same as drive, the belt crosses each other. There is a lot of wear and tear. Okay, so this type of drive should be used for larger distances between two shafts and for lower speeds, right? And in this case, your angle of contact for both pulleys is the same, right? So even when the diameter is not the same. So here you can just find doesn't really matter which one we have to use. You can just find the angle of lap for this, and then we can get that. All right, so here we go. So is there any questions so far? So I think that's a lot of information. But is there any questions? Any unclarity? Students, they're still sleeping. Brent, Mr. Silver, Ivano, Matthew Doyle. There you go. Tommy, you guys awake? Yeah, thought so.
No, so I'm awake. I'm awake now.
Yeah. Great. Okay, no, just information, guys. Just relax. I'm nearly there. Yeah, it seems like I'm not nearly there. Oh, well, no, I am. Which is example 1? Yeah, it looks a bit far. Yeah, okay. So what the idea here is, right? So we have to consider a belt, drive partially. Mr. Mzam, go for it.
Yes, sir. I have a question here. I want to know which one is the which one is the driver here?
In this particular one I'm looking at now. Yeah, the small one.
Oh, okay. Okay.
Yeah. So small one is always the driver in this case. Well, it seems like it is anyway. Okay, cool. Thank you for the question. So when you're looking at the analysis here, what we just have is a pulley, and we've got the belt around the pulley, right? We're assuming a rotation over here, and then now we're looking at all the forces acting on it. So, of course, what's important is that the pulley on either side, sorry, the pulley, the belt on either side has its own tension, and as it's rotating, and if you look at the top now, we have it splits, of course, the forces into the components due to the angle there on top, right? I mean, as we go along, there's not much, because I'm not mentioning the centrifugal force yet. I don't want to get to that. Use a bit of integration over there, and bam, 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 and we end up with the ratio T1 T2 equals Euler's number to the power raised to the power of the coefficient of friction to the angle of lap. So that's what it essentially is. But the idea is that you look at all the radial forces, right? Forces to the left and right, the horizontal, and we get the tangential force, which is all the vertical forces. And of course, that will do, in this case, you get the frictional forces, the tensions at this particular angle on the one side. And I mean, just basically considering a small angle, we're going to end up with that model over there. So that's a very important equation. The tension of 1 equals tension of 2 equals Euler's number E raised to the coefficient of friction to the angle of lap. All right, very important. Okay, so we're getting there. That's just a nice table telling you exactly what each variable means and the unit you should be using. So that's fantastic. I recommend looking at that. But now, because we're dealing with a rotating system, you've learned of a new force. The forces are the centripetal, the centrifugal force, or centrifugal force will be the inertial force of the centripetal force. And we have to take that into account when we're doing analysis. So what does it say? This expression, which is one above, does not take into account the centrifugal tension. For low belt speeds, Tc, which is now centrifugal tension, has a little effect on the power transmitted. Obviously, you know, the velocity is small, it's somewhat negligible. But as we increase, as it says here, so however, Tc is a function of the centrifugal force mv squared over r. You guys are experts on that, which increases to the square of the speed. And since the polar radius r is always less than 1 meter, the centrifugal tension has a marked effect on the ability to transmit power at high speeds. So even though we're going faster, and this is why you probably have limitations with this kind of system, is that the centrifugal speed could snap the belt. And that's what actually snaps the belt. One of the reasons why. So what do we just basically do now? Okay, I should actually go start over here. Same model, so T1 over T2 equals E to the power mu to the angle lap. All we do is say minus Tc on both of T1 and T2. Very simple. We're just adding that now. To compute it, I'll have to show you how to compute that. But essentially what it is, slides are not arranged like here. I just pick up now. To compute the centrifugal tension, is basically your mass times velocity squared. And I'll come back to this because this was not supposed to be here. What's supposed to be is a power delta, right? So how do we sorry about that. So what's important over here is the power. Your marine mechanical engineers, when you always want to talk in terms of power or watts. So of course, what happens here is, of course, we're getting torque. and we normally times it by omega. And in this case, we can just go force times velocity. And this is a nice illustration again. So as again, we have the driving pulley and the driven pulley. No man, driven, what's driven? So the small one's being driven in this case. Yeah, so I'm getting a bit confused here. Nevertheless, to find the power, so the driving pulley is the bigger pulley here. So just bear with me here until I get all that in order. As it rotates on the top side, you get the slack side. There's lesser tension compared to the bottom side, which is the tight side. And essentially to find the power, that's going to be the difference of T1 minus T2 times the velocity, which will your linear velocity, and that will give you your power. Okay, so just to recap all of this, what's important over here is your new model for calculating the tension in the belt. So it's T1 over T2 equals E to the power mu times theta, and that gets now modified with centrifugal tension. So we have T1 minus Tc over T2 minus Tc equals the same on the right-hand side. And of course, what we have to do now, same with our power. So let me just quickly show you how this is a convenient form to use, which you kind of use a lot. So we said power. I hope you guys are finding this color. I never talk this much, you guys. We normally do an example, but it's fine. It's fine. It'll all be worth it. Power equals, I said T1 minus T2 times V. So we basically use, I'm just illustrating to you how we get this formula over here. So T2 would be, so T1 equals T2 times E mu theta, and then we divide this out, and then we have this eraser here. So T2 is equal to T1 over you know that piece over there. Just want to move on. So power equals T1 minus, sub that guy in, T1 over E mu theta. So just a quick illustration. And of course, we can take T1 as a common factor. We have 1 minus 1 over E. So this is a normally convenient form because all you have to do is just basically find your first tension. Sometimes it's given, you have to work it out, and you go 1 minus that. So, and then with your centrifugal tension, exactly the same setup. Is it clear to everyone? That should be the formula. Yeah. Is it clear to everyone? Can I move on? Can we go first example now? Oh. Clear? Are you guys okay? Mr. Mzam? Can I get a thumbs up there before I move on? Now I'm going to be solving examples now. So fantastic. I'm confused now on which is the driver and which is the driven because the slide showed a few seconds. Yeah, that's what I'm saying. Don't worry too much. We'll figure it out. We'll figure it out. Like I said, drive pulley, driven pulley. So I think let me just make sure about what's happening here. Yeah, so the driven pulley, so the drive pulley is going to, so okay, so the big one is a driver pulley and the small is a driven pulley. I'm not sure why I would think that the other one is the other way around. So let's go big is a driver and the small is a driven one, right? We just keep it like that for now. You'll figure it out.
Okay, cool.
Yeah, I'm sure there's a reason why, and I'll get to it. I just lost my train of thought. Okay, so there's your first example in the book. So I'm just opening my whiteboard. If you do have your formula sheet next to you, I recommend getting it out because that's your bread and butter, I guess. All you have to learn from the section, my students, is that know how to apply the formulas. It's really a nice section if you understand what's going on. It can be either one, the question or state. Oh, thank you, Mr. Kiefer. Always allowing that, man. Okay, thank you very much. Let's just get going on this. Yeah, I give examples. It's easier to express oneself with examples and versus words. Okay, this is the first example. It's on G12 in your notepad, and this comes from the book. I'll show you the stuff here. Anyway, never mind. You need 2 questions, right? Question is 2 pulleys, 450 millimeters and 200 millimeters in diameter, mounted on parallel shafts, 1.95 meters apart and connected by a flat belt. A, find the angle of lap between the belt and each pulley and the length of the belt in the belt if motion is transmitted by an open belt, right? So we know what an open belt, flat belt, open type arrangement. 2 is how much power can be transmitted when the larger pulley rotates 2000 revs per minute if the maximum permissible tension in the belt is 1 kilonewton and the coefficient is between the belt and the pulley, of course, is 0.25. And then repeat exactly the same for crossbar. Okay, so what does it look like? Just get that ready. Okay, so there's around 8 examples here. Ideally, I'd love to do all of them, but if I don't, you just have to make sure you go over it. But I think we have enough time to cover everything today. Let me just open. I don't know. Get the diagram for you so we all it looks neat. So please check on the Blackboard. Of course, I've posted additional notes. You should always go over them, and that is from the Theory of Machines book, which I always refer to. Okay, so that's our diagram over here. Okay. So maybe we can now bring out understanding of what's happening here. Okay, well, just forgive me. Yes.
So you're on Blackboard, on the whiteboard now at the moment? Oh.
Yeah, I know. I am. I'm going there now. I'm just preparing so long.
Oh. Oh.
Yeah. But thanks. I know. I'm away. I'm going there now. Yeah. I'll just question the stuff in the meantime. Okay. I'm sharing it now. Okay. So this is what our range will look like, right? There's a picture here. Okay. So we've got a big pulley, so-called the driver, the driven pulley. And we've got the center distances, right? That's very important. And we've got the diameters over here, right? So, like I mentioned to you, well, so our objective for this particular problem, I'll back it now, is A, the angle of lap, and the length, right? So conveniently for us, we've got the 2 formulas there. Where are they again? So this should be negative. Yeah. So you need to know how to use each one, essentially. Okay. So that's for the length. Of course, for this, we have to use the other one again. Sorry. Let's snap that also. Fairly easy. Let's just quickly look what's happening here. All right. So simple, right? Plug and play. So just understanding of how it all comes out. So remember I mentioned we have to use the angle of lap on the smaller pulley, right? Slip is going to occur here first. So we always the theta, whatever theta is, theta, what we're looking for is that guy. So how do we find it? What they actually do over here, if we have a right angle triangle essentially, and we use the distance of the driver pulley, it's going all the way up, and then we subtract the distance of the smaller one, right? Which is that over there, and then we're left with this, well, the radius of the smaller one, right? Which is that. Then we're left with r minus r, right? Simple tricks again. So it's opposite. Sorry, this is my adjacent side. Adjacent is over here. Hypotenuse is over. Hypotenuse is here, right? So, but of course, this is only half the angle on the other side. So what it actually looks like is we can have it like this. So let me just shift to A. Like that. Cos, what am I doing here? So it's cos theta over 2. Remember, it's always going to be the smaller one anyway. Then that's going to be r, big R, I'll just call it big R minus small r over C. Cx, all the same thing. X is just the distance between the two shafts. So to find the angle of lap, we could. Just give me a second. We can use the radiuses, radii of the two pulleys. So the first one, that's 450, divide that by 2, you get 225, I think. Minus the smaller one, that's 100. And then it's divided by the center distance. So that's going to be 1.95, right? Remember what's important is this is only for a flat belt, right? You deal with a cross belt, but the formulas look the same, but you probably have to have a few signs are going to change. Just be aware, right? So know what to use for what particular situation. All right, so can we just quickly compute that? That's 64.102. Are we allowed to do that? Am I on the right track? I feel like I'm off somewhere. What's my angle? It's 1.95. What am I feel like I'm looking here. Just to see, just give me a second. Oh, I see. Just bear with me. Bear with me. She's supposed to be in millimeters. That's why. So that's what it is. Okay, there we go. Got it. I'm using millimeter. I'm using all in millimeters, and we should get 86. Yeah. Should get 86.325, and then times that by 2. And we should get 172.649 degrees. Now it's important here is to make sure that we're converting this into radians, right? So this one's we're converting to radians. Of course, that's pi times pi multiplied by pi over 180, and we should get 3,0133 rads. What's important to always remember when you're finding the angle of lap, you need to always have it in radians. That's very important. Not the groove angle. The angle of lap must always be in radians. So there we found the angle of lap, right? So if you look at that diagram, it's around 172.649. That's basically the belt is basically surrounding it. If you want to think of it like that, it's nearly 180 degrees. Obviously, we can look at it. So we're like a few 8 degrees off. That's basically, I could just sketch this for you. It's as soon as it layers, like for instance, it's this angle over here. Okay. Of course, this this one is 172 or around 173 degrees, which looks really okay. It looks like 180, which is close. Okay. The next thing is to find the length, right? So now, yeah, I gave you a nice formula. Fortunately for you, you could have done it the other way, and the other way is essentially looking at. I just want to show you, so you don't. We take, we add this length from here to here. So we have this length from here to here, the length of the belt here to here, there to there, and then we add on the driver pulley, and then over here we add that length from here. So of course this is going to be like, S equals radius times that. That's also S equals radius times that, and of course here we have the two lengths. So I think that's 2L. So one way of writing it out, and I'm not using the formula now. It's going to be length equals 2 times L, which is of course which I just did now, plus R times theta, which is the small side, plus big R 2 pi minus theta, which is that's of course 360 degrees. So just looking back at this, so it's the length here, 1, 2 for the top at the bottom. The smaller pulley, of course, that's R times theta, which I've done there. And of course on this side, because we're looking at this angle now, we have to say, of course, 360 minus whatever that is there. So that's one way of doing it, right? But simply what I find acceptable is you can just use this value, which is essentially the same thing as this over here. So I like you guys to find the length of this pulley for me, the length of the belt for me. So of course over here, that's your two diameters, and that's your X would be your center distance C or X. You can depends on how you wanna what do you wanna call it. C or X is perfectly fine with me. So can you just quickly find the length? So you have the two diameters. You've got X, which is the distance, and let's see what you get for your length. Let's see what's close enough to what they have over here. Okay, I'll give you guys like 2 minutes to do that. Plug and play. All right, so that's conveniently done for you. So that's fine. But what I want to touch on now is where we need to get the meat and potatoes of this thing. So at number 2, I'm labeling this A and B. It's not the correct labels. That is really important. Let's just get it right. Okay. We get the idea here, right? So number 2 is how much power can be transmitted with a larger pulley. So it's telling you rotate at 200 revs per minute if the maximal permissible tension in the belt is 1 kN. All right. So where we heading to is power equals T1 minus T2 times velocity. Of course, like I said to you, we can change this up and say T1 1 minus 1 over E mu theta times velocity, right? Force times velocity, if you're ever just wondering what's happening. Okay, so of course, what we need to do now is find the individual things, well, the velocity and that guy here. So now what we normally do is we can just say, we can go T1 over T2 equals this. If you want to do this, T1 over T2. So we know E, what's our coefficient of friction? I think it was 0.25. And our angle of lap we've worked out, but remember it must be in radians, and we have it in radians. And that was 3,0133. And we can actually just get that guy quickly in our calculators. Then we get 2,124. 2,124. T1 over T2. Okay, which is essentially that, or what's 1 over. So we have this value here. It's fine. How do you think? The tension, oh, they say the maximum. They really want the power. There's nothing else to want. So now they say the maximum tension in the belt is 1 kilonewton, and of course that's going to be on the tight side, right? So it doesn't really matter where it's rotating in this case. But all we have to, and of course, what we're missing here is one more thing, and that's the velocity. Not just write the velocity here. So we of course know pi d n over 60. So it's pi times, they said the larger pulley, if I'm correct, is rotating. Yep. And that's at 200 revs, and that's at 450 millimeters over 60. And then we can get our velocity. We can quickly do that. Wait, give me a second. Something is, oh, times 10 to negative 3. I'm being a bit. So pi times 0.45 times 200 over 60. That's 4,712. 2.3, right, or 2.4. Acceptable, that's acceptable. So we have that, so we say P equals, so T1 will be the, like I said, it's the maximum permissible tension in the belt, which will be on the tight side. So let me just quickly erase this. And so if this is rotating this way, all right, this become your T2 on top, that becomes T1. And this is rotating, omega is going to be at 200 revs per minute, right? Okay, so and T1 is equal to 1 kilonewton. So that's 1,000, so 1 kilonewton. 1 minus 1 over whatever that guy was, 2,124. I hope I got that right. Yeah. And then eventually you have to times it by the velocity, which is 4,7124. Can you guys quickly compute that? Oh, sorry about that. Is it the power? Yeah, 2,4. Yeah, thank you, Mr. Kiva. 2,493 kilowatts. I'm just missing something here. Yeah, 0.75. Yeah, around here. Okay. So like I said to you, you could have also done power equals T1 minus T2 times velocity. So if we do want to find the tension in the the slack side of the belt, someone said something. Yeah, it's fine. It's close enough. It's close enough. But it's fine. I know it's 3 more, but yeah, I got the idea. Will be simple, and T2 will simply be T1 divided by 2, comma 1 to 4. And if you get that, you should get around 471 newtons. So just stepping back and looking at the analysis, T1 is 1,000 newtons. T2 is 471 newtons. And our total power without slip here is 2.49375 kilowatts. Just give me a second. We still have another hour or so, but I'm going to touch on the cross belt, and then we can actually move on to all the interesting stuff very soon. But this is a general idea of what's happening in the problem. But we'll get into where we need to be. But let's just take a quick break. I know it's a bit of information, but like I said, guys, it's a very easy section. Just have to know how to use your formulas, and you should be more than adequate. Okay. I'll see you in the next 15 minutes, 10 to 15 minutes. Thank you.
So when you come back, can you please explain this question number 2?
Which question?
This one you just did. Can you please go over it when you come
Again?
back? Yes, sir, because I think I'm confusing somewhere. So I want to understand. It's already going.
Okay, that's fine. Is it fine? You ask the questions when we get back, no? That's fine.
Okay, cool.
Okay. Right, we're back. Are we all here? Students, are we all? Can we go? Mr. Zam, you had a question? Mr. Zam. Let's see who's all here. Annalisa, Aaron, Brent, Mr. Silver, Mr. Neto, are you guys here? Back. Okay, great. Let's get going. Mr. Zam, where's your question before I move on? I just saw Mr. Boy now, so I'll be getting the scripts today, so hopefully I can resolve all of that by this weekend. Hopefully. Mr. Zam, where are you, man? So I need to move on. Okay, guys, so what is your question? Okay, just collecting yourself. Okay, guys, so can I move on here? All right. So in the next question, part of the question, we have to repeat if this same if this open belt is replaced by a cross belt, right? So we still a flat belt, but now we change the range to a cross belt. So the cross belt, the pulleys are rotating in different directions. I just want to get that particular image for you so you guys can have a look what it looks like. Just give me a second. So you see the way you have to think about this is that you must identify what kind of belt it is, whether it's a flat belt or a V or rope, and you have to use the equation and what kind of arrangement it is. So that's very important of this kind of question, or of this particular section, sorry. So in this case, we're dealing with a cross belt. And now, like I said, we have new, well, the formulas are essentially the same, but just okay, so what is it? Is it anyone saying something? What's going on here? I had a problem on mics. Okay, oh, grandson Zam. Okay. Let's see what we can do. Okay, right. So it's the same setup here. So we want the angle of lap here. So the angle of lap in this case, our formula now is good. Oh, just give me a second. How we tackle this normally is that theta will equal 2 pi. Of course, this in radians minus 2 phi. It's exactly the same as this over here. So for us to find phi, we're going to have to say cos is going to be R1 plus R2 this case, and that is 225 plus 100 divided by 2. So it's a similar setup. So if you look at this, just scrolling towards this thing, we're still using trig, so it's still opposite, sorry, adjacent, which is this. So adjacent will be this whole triangle over here, right? That's R plus, big R plus R. And then of course hypotenuse, which will sit over here. So the hypotenuse is basically the whole distance from here to here. Whoa. Oh man, this is really not working well for me. I have to probably go very slow. From there, that triangle over there. So you just to illustrate you where it is. so that you know, but you don't have to worry too much long, you know the formula is, right? So we're going to get phi first, and that's going to be 80.41 degrees. And if you convert this guy to radians, you should get 1 point.
Sorry, sir.
Yep.
So you're not supposed to divide by 1.95.
1.95 for radians.
No. For your theta, sir.
Oh, sorry,
That is the
sorry, Chief. Thank you.
one.
Yeah. Thank you, Mr. Romanus. Yeah, here we go. I was losing track of what I need to do there. Plus, yep, and you should get 80.41. And of course, you have to multiply the guy by 2 as per the previous one again. And you should get, sorry, man, 160.81. And this must could be converted into radians. So that is fine. That's fine. You could forgive me for that thing. And if you do that, you should get how many radians? 2,801 radians, right? So we've got that, but we have this angle now, right? We have this angle over here, 2 phi, and for cross belt, the angle of lap is exactly the same. So we can use either one now, right? So the slip would be a slip can occur either on the driver or the driven. And the simple thing, all it essentially is, we could have just done phi could have actually just been 360 minus 160.81. I'm just doing it like that. You've got 199.19 degrees, or you could have just said 2 pi minus 2,801. Same thing, and you should get 3,476 radians. Are we all happy with that? So I'm just making you aware when you're dealing with a cross belt, when you find the angle of lap, it's a different kind of setup here, right? So just be aware of that. Cross belt on the same shaft, 2 different rotations. Whereas a pulley, it's 2 same rotation, same 1 shaft. Okay, I hope that's clear to everyone. And then again, to find the length. So the difference between the cross belt and in terms of the formula, just as a comparison, that one. So, and of course you have to know this, but I don't actually tell you. I actually don't tell you this. Is that instead of minus now we add, right? So we add the distances now. We add R1 plus R2 basically to find the length. So if we do that, I still don't actually do all of this, but anyway. So diameter is 225 plus 100 plus 2 times 1950 plus 225 plus 100. And we square that guy and say 4 times 1950. What is my length? Let's see what we get. So you can see it's just all knowing what to use in what particular context. It's really not that bad. So now you've learned flat belt, and you've learned cross belt to find the lengths and stuff like that. Okay. Is this correct? Do I have this all right here? Did I make a mistake somewhere? I'm not particularly sure what I did wrong. Pi over 2, the diameters 2 to 5. I think I'm making a mistake somewhere. I can't tell it. Can you guys just compute the length for me quickly? I'm using this formula here. The length is supposed to be 4.975 meters. That's the total length of the belt. Supposed to be that value.
Sorry, sir. Why are you using radius instead of diameter?
Oh, that's why. Thank you. And you was out something. Okay. Fantastic. That's what I want to hear. So it's 450 plus 200 and 450 plus 200. Okay. And of course, if you do that, you should get the correct answer. Okay. Interestingly enough, we also need to find out the power transmitted for this, and it's exactly the same. So yeah, 4975 on the dot. It's fantastic. We've got the length of the dot, exactly the same as in the book, even though they use a different approach. So now power equals T1, 1 minus 1 over E mu theta times velocity. T1 is still 1,000, 1 minus, but the difference is now our angle of lap. And our angle of lap, it has essentially increased. And if we plug, it's 3 times 3,476, we times the velocity, and the velocity is exactly the same as 4,712. And if we find power, we get 2,74 kilowatts. So of course, I mean, it's the same calculation. You don't actually really have to obviously do it. But what's important to note, if you had to use a cross belt for the same kind of arrangement, you'd receive more power. But of course, it was obviously depends on application. So if you cross belt, and that's for a flat belt. So it's the same formula. Don't worry too much. Still the early stages. So yeah, is there any questions before I move on? Anything, guys? Please. Now we're just going to add the centrifugal tension now. Right? It's going to get fun. Now you've got a few skills now. You'll be able to figure this out now. You'll see. Nice and easy. Good 15 to 20 more questions. Any questions? Can I get like 3 or 4 thumbs up before I move on? So just important again, guys, I can't reiterate this enough. Please, please, please know how to use the formulas. That's all you need to know. Understand what means what. But after, if you do a few of these examples, yeah, you've kind of mastered the section. It's a very simple section. Can I get one more before I move on? Any questions, guys? Here you go. Okay, thank you, Mr. Mutang. Let's move on. Let's see here. Okay. So now that you have a bit of experience with belt drives and did a bit of some analysis on it. So I shouldn't go back to the previous slides again. So let's see what we essentially just did now. Using this model here to find the tension, to find the power. But now we're going to grow up and start applying the centrifugal tension, which we have to subtract. So, and if you look at the actual diagram, in terms of centrifugal tension, it acts obviously over here, and we even got a frictional force due to that. What's also important, if you are lost with your variables, this table is a fantastic place to just orientate yourself. Exactly what, depending if you need to know what each variable means, it'll tell you the unit, and it will tell you exactly the symbol as well. Right, so I mentioned to you about centrifugal tension. So it says, again, this is just the basic analysis. As again, we're just taking horizontal forces, that will be the radial ones, and then the tangential ones, which is the vertical ones. We're just doing forces up, forces down kind of setup. Again, but in essence, what we end up getting is your centrifugal force equals your mass times velocity squared. Now, what I find particularly strange of this, your mass normally is per meter length of belt, so kilogram per meter, right? We always work like that, even though we don't times by the actual length of the belt. So I just have to kind of, so let's say if the mass of the belt per unit length, so you're always gonna end up finding your mass is per meter, and then we just work per meter essentially. We don't really times by the length of belt. Okay. It's again exactly the same thing. It's just adding all the forces. Just to now, maybe a bit more mature, we can look at it. So we've got R, F, the frictional force plus R, that would be the reactional force, and that is, so let's look at where's the other one, and this is equal to, just give me a second. Okay, yeah, so essentially, like I said, all what happens is we end up with the same formula, but now minus the centrifugal tension. We lose a bit of tension or force due to it rotating. Okay, I'll come back to this, the initial tension. So I'd rather let us do an example based on. So what's new here is that now we've got TC, right? So I'm going to do one example, and I'm going to give you one to practice with. But it follows the same vein of the same kind of setup, basically the same procedure, if one could actually just say that. So what I'm introducing, what's new here is just the centrifugal tension. The initial tension part here, I'm gonna have it afterwards again. So just bear with me, guys. I should have I'll throw it at the bottom here somewhere. I'll throw it after with maximum power transfer. So just give me a second. Okay, guys. So I'm gonna show you this example, then I'll give you one practice, and then we can actually move on. Okay, so my whiteboard quickly. So now where we're getting to is what we're like 50% of the way there, in terms of 50 to 60% of the way there in terms of how you'll be assessed. Like the hardest problem of so-called this belt drive stuff. Okay, so how do we start? So we've got a pulley with an effective diameter of 200 running at 1,000 revs per minute, drives a second pulley with an effective diameter of 1 meter. So can we just quickly get that? So a pulley, that is going to be, let's say 200, omega is 1,000 revs RPM, and it drives a second one, which is 1 meter. So you can see with Zam, it's essentially dependent. Just my pulley here. Yeah, so this guy's, let's say, is 1 meter. They're mounted on shafts, which is 1.5 meters apart. So the center distance 1.5, right? That's in case you might need to find the angle of lap. They say the tension in the belt may not exceed 800 newtons. Once again, if we're assuming it's rotating clockwise, yes, this becomes T1, that becomes T2. So slack side is on top, and we know that T1, it's the maximum amount of tension, so that be 800 newtons. Of course, if we exceed this tension, the belt will snap. Then it'll give you, it says, and it has a mass per unit length of 0.4 kilograms per meter, right? You'll see what I'm talking about. So we know the mass per length. And if the coefficient of friction between belt and pulleys is 0.4, find the power transmitted, right? So holistically, where are we? So when you find the power now, that's going to be T1 minus TC times 1 minus 1 over E U theta over times the velocity. Remember, this is also just the same as T1 over Tc over T2 over Tc equals that over there. So we just make it easy so we don't have to put too many variables over here. But if the question does ask to find the tension find both tensions of the belt, it would be very important to do that. So obviously that's fairly easy. So our unknowns for this particular problem is your angle of lap, our TC. T1 we have, and then our velocity we can easily find, and our velocity, of course, which is our linear velocity of the belt. Now remember, it's not slipping, right? The belt is not slipping in this case. And the belts are slipping, our velocities are equal to each other. But let's start to unpack now. So this is a flat belt pulley. Which formula should we use now to find our angle of lap? You remember? For you guys. So flat belt, that's the formula. Are we all happy with this? So can you see it's a common way of how we're going to start the problems, right? You find angle of lap. Sometimes they actually give you angle of lap, so you don't have to find it. So let's quickly do this. 3 over 2 is going to be equal to something over here. Let's just quickly see. So we have 100. Oh, the big one's 500, right? Minus 100 over the center distance, and that's 1.5. 1,500. So 500, big one minus small one. Of course, this is now, let's say, I'll cause this, right? 74.54 degrees. Correct? From right there. And of course, you multiply that guy by 2. And we get 149.06798 degrees, right? And of course, we can convert that into radians, because our angle of lap is always in radians. I think I'm fine here. So 2,60172.73 radians. Are we all happy with this? Very important, right? You probably get around 2-3 marks for the step. Are we all okay here? Remember, this is for a flat belt. A flat belt. It's flat belt. And the arrangement open. Open arrangement. So you can have flat belt and then crossed. So are we happy with finding the angle of lap? Are there any questions? We'll see you.
Yes, sir.
Any questions?
So far so good. Sir.
Yeah, it should be okay. Take a moment to resolve. Okay, fantastic. Thank you, Simelo. So what's next is, so we found one variable. Let's just tick that guy off there. Now we're going to find the new variable, the so-called centrifugal tension. Now I'm making you aware. So this looks funny enough familiar to, remember your rotational hoop stress, the rho v squared, something similar to this, right? So just making you aware, it's essentially the same as that. And if always wondering why is there a v squared, let's say centrifugal, remember mv squared over r? Very important. Square of the velocity. So, like I said, we just work per meter with this, so just bear with me. So we just take, let's just take the mass per meter, which was 0.4. And now I have it times by the velocity squared, right? So the velocity in this case it should be simple. We've got the driver here, and the driver in this case is at 200 millimeters at 1,000 revs per minute. So we can go pi times 2,000 times 1 over 60. We square it. So right. So guys, I'm making you know, just treat this as kilogram, right? Even though it's kilogram per meter. We can actually find it. We just work per meter. No question really asks you to find the length times by the amount of. There's no need. Most of these questions don't require. So anyway, we find centrifugal tension. We should get around 44 newtons. Let me just quickly check. So like I said, we're getting there. You're getting a feel of what this whole section is about. Yeah, we get 43,86. That's the exact amount. I thought these values are. So can you see it's quite small? So but we lose a bit of tension there. 43,865 newtons. Okay, so once we have this, we have to go back to our power formula. So remember, we have to subtract the centrifugal tension. We lose a bit of load there due to the centrifugal force, and that gave us our limit. And I think our limit was given at 800 newtons. So I would like you guys to compute that quickly. I'll give you guys 2 minutes. Get the power. So can you please just get that? Get the power. Let's see if you're able to get it. Okay, guys, you get the power. Should have been easy to compute. Students, we're giving up. Let's see. Hello. Oh, Alisa got it. Yeah, that's fantastic. Okay. Can you guys hear me speak? I'm using these AirPods, so I'm just. Can someone say something?
Yeah,
quickly?
sir, I can hear you speak.
Hello.
Hello, sir, can you hear me?
Am I clear?
Yeah, you're coming through very clear.
Yes, sir, we can hear you quite fine.
Can you guys hear me? Okay, so I'm using AirPods now, so I don't know if is my volume the same or. The reason why I'm doing this, I'm trying to actually like. Oh, fantastic. Can you guys speak? Can you guys say something quickly? Mr. Mzam, Mr. Kiefer, if you don't mind.
Hello, can you hear
We
us?
can hear you, sir.
Are you guys saying something?
We are saying things, yes.
I can't hear you for some reason.
Yes, sir, we're saying.
Are you saying something?
No, we're not saying anything, sir.
Matthew, are you speaking there? Oh, let me go over here and check the yeah.
Yes, sir, we
Yeah,
are
I
saying
find it
stuff.
quite strange that I can't hear you guys, but you guys can hear me. Why would it be? So I got headphones in. I thought maybe that'll change something up. I don't know why this one will work. Okay, that's weird. So I got to check that out. So let me just disconnect here. Yeah, I thought. I'm not sure why I can't hear you guys, so that's a bit weird. Okay, can you guys speak now? Matthew?
Hey, sir, what's up?
Yeah, so yeah, I was just checking AirPods. I thought I somehow can't hear you guys speak, but you can hear me. You guys wonder why? Anyway, that's weird. Okay. So to compute the power will be a fairly simple process. We've got the maximum tension that's 800. We have to minus the 43,865. 1 minus 1 over, to be fine, oh, we still have to find all of that, so that's E to the power 0.4 times our angle of lap 2,60173 times the velocity, and the velocity in this case was 10.47 meters per second squared, and if you get 5. Fairly simple, guys. I promise you, it's a very nice section to do. 5.1195. Okay. I'm just kind of quite sad that I can't actually hear you guys. It's quite weird. Okay. All right. So I've done this one. Time is hitting us here. Let me just go back. Let's go check. So we're just basically going to do another one now. Where am I? Here. It's example 1. For example, okay, let me go back to the slides now. Yeah, so I have to go back to the slides here. Okay. All right. Okay. So yeah, so now we have a bit of experience with belt rise and some with centrifugal tension, a bit of centrifugal tension. And now, Mr. Mzam, yes.
So also like about the pulleys, we're
Mr. Mzam.
trying to get which one is the driver and which one is the driven. So
So
do
it
you hear me,
doesn't
sir?
matter. Yeah, so they will tell you which one is the driver, which one is driven. So the question was
Yes, sir.
straight,
Yes,
like
sir. Okay. Okay.
the previous one. Let's just look at it quickly. Previous one, yeah, it says the driver is so a pulley with 200, which is the driver, obviously is running at 1,000 revs. Drives a second pulley, which is 1 meter. You see there. So you've got a small
Yes, sir.
pulley driving a big. Yeah. So it depends. It will change on the nature of the question and the context.
Okay.
Okay. Of course, with more examples, you can actually see this.
Okay, sir.
So guys, what's also important here is something called the maximum power transfer. And let's just quickly read exactly what's happening here. Now it states that now the tight side tension T1 has an upper limit which may not be exceeded. Of course, we've kind of been highlighting this, or the belt will be overstressed. Overstressed means essentially to fail, right? That's what actually happens when the belt breaks. Of course, it gets worn out and breaks, but this is okay one. In fact, what actually happens is on the belt drive itself, as you use it over time, the stresses produced from rotation and of course tensions, the inherent tensions in the rope, it produces fatigue within the belt, and then only after a certain amount of cycles the belt will snap. Anyway, nevertheless, so the belt velocity V can be varied while maintaining T1 at this upper limit to some lower fixed value. Then the maximum power to be transmitted, the differential power with respect to 0. So of course, you guys always remember when we're taking when we're making the derivative 0, you think we're always finding the maximum value. So if you think about your, just as a mathematical background here, not really that I have to do this, but you know, if we take, hope you guys remember your maths, a simple quadratic equation. If you remember the turning point formula, I think it was x equals minus b over 2a. And if we take dy dx, you will get 2ax squared plus b. And to find the maximum value, which is the turning point, to make this equal to 0, we have 2ax, so it's just 2ax, not 2a squared plus b. You carry over the b, and you minus 2a, and you have x. So always remember when you're taking the derivative and you're making it 0, you're finding the maximum power or the maximum, the highest point in the graph, whatever. Okay, so what essentially happens after taking the derivative of the power is equal to this, you've seen it before, you end up with two relationships. And what's important is that for maximum power to be transmitted, your centrifugal tension must equal a third of your initial tension. And of course, if you want to find the velocity at which that occurs, it's simply going to be the velocity equals root T1 3m squared. Where this essentially comes from is that centrifugal tension is mv squared, as you've known. That equals T1, and all we're doing is dividing by, and of course this is now a third. We're dividing by the mass, and we're just taking the square root there, and then we're left with the velocity. So these are also given in the formula sheet. So this is only for the maximum condition. So when you want to find the maximum, what's the maximum power you can actually deliver, and what's the speed at which that will occur, that is the two new models or equations you have to use to solve the problem. All right. So let's just quickly, just go back. Okay. So that's the one new thing. Okay, I'll just leave that there for now. Another thing is the initial tension on the belt. So we've been discussing this, but this is normally when you're looking at the force on the bearings itself. But just quickly in summary, to kind of conclude this, the theory part the lectures. So they're saying when a belt is around 1-2 pulleys, the driver or the follower, so we should call it that. It's 2 ends of joined together, so the belt may continuously move over the pulleys, right? Since the motion of the belt from the driver and the follower is governed by a firm grip due to friction, obviously, between the belt and the pulleys. In order to increase the grip, the belt is tightened up. At this stage, even the pulleys are stationary, the belt is subjected to some tension. So the idea is there that there's some initial tension on the belt, which we have to account for, which we obviously do. But what they're basically saying here, just as a quick new thing, you just have to be aware that when they give you some initial, this is not very common, but that initial tension is essentially equal to T1 plus T2 because 2 times the initial tension on the belt. And then this just arises from, so what they're saying is that when the driver starts rotating, it pulls the belt from one side, increases the tension on the belt on the side. So if it's basically on the tight side, we're getting an increase in tension and delivers it to the other side. Yeah, okay. Decrease the tension on that side of the belt, that's the slack side. The increased tension in the one side of the belt is called the tension in the tights. Okay. Yeah. The idea is that we have when the belt is subjected, there will be initial tension in the belt, and it will basically be the average of T1 plus T. It's basically the average of the tight side and the slack side. And if there is centrifugal tension, we have to account for that, and then we do. So this is not always common, but it does come up sometimes. All right. And then we can solve more problems now with V belts, maximum power transfer. That is what I actually want to do. Okay, so let's get example 3. Where is example 3? Maximum power transfer, initial tension. And there we go. Yeah, I need to just kind of fix up my slides here. I didn't arrange it the way I want to do it. Okay. Let's look at this maximum power transfer setup here. All right. Okay. So I'm just going to go back to the whiteboard. So just the new thing is that the belt is initially tensioned. Sometimes you account for it, and then also we've got a maximum condition for the in terms of the tension and in terms of velocity. Okay, so we're going to be solving this problem. Next. Okay, we've got a few more minutes left, so yeah. All right. Should be enough to get you ready for the test. Okay, I've shared that. This is example 3 in your notepad. So the reason why I like this problem, because now we have to find the initial tension. But let's see how it goes. So we have a leather belt, 180 wide and 10 millimeter thick, makes contact with 1/2 of the circumference of a pulley, right? So 1/2 of the circumference of the pulley. When I hear that, I think pi equals 180 degrees. Okay. Pi, well, sorry, the angle of lap is 180 degrees, which essentially equals pi. Sorry. The greatest permissible tensile stress in the leather is 2 megapascals, and it has a density of 1000 kilogram per meter squared, and the coefficient of friction is 0.4. Find the speed at which the power transmitted is the maximum, and the maximum power can be transmitted. Like I said, we know now TC must equal T1 over 3, and this is going to be the velocity. Let me just get this formula in, which essentially will be what's the speed? We could just say TC over M, right? We can find that speed. All right, let's get cracking here. Okay, so first thing, right, we need to find the initial tension. So I like this problem because now you're not actually given T1 and you have to compute it now. So, but we know that force equals stress times velocity. In this case, we can say T1 times stress times the area. So the maximum allowable stress in the belt, tensile stress obviously, is 2 megapascals in this case. And now we have to times the belt's dimensions. So we have 0.18 times 0.01. Great. Now, what's cool with this problem, sometimes they might ask you to find the width of the belt or the thickness. So I'm making you aware that sometimes you find T1 as whatever value it is, but then they give you the stress and they give you the thickness, and they request what's the width of the belt. So I'm just making you aware that they can play around with particular, with the dimensions and the stresses level. So once you find that, you should get 3,600 newtons. Okay, and it's a fairly simple problem. So for maximum power conditions, so we say for maximum power conditions, for max power conditions, this is like an extra throw in there, normally in the, we know that TC has to be equal to 3,600 divided by 3, so T1 divided by 3, and we find out the centrifugal tension will be 1,200. That's the max amount of centrifugal tension we can get. And of course, we know that TC equals mass times velocity squared. So they wanted the speed, right? So we're looking for V. So for the mass, we have 1,200. So I say mass is density times volume. And because you're working per meter, we just need the area. So we have to take the density. So 1,000 times 0.18 times 0.1. So then we're working always per meter here for some odd reason. So this will be, what is this? 0.18 times 0.01 equals 1.8 kilograms per meter. Once we have the mass, we can just throw it over here, and then we can find out the velocity. And then we can say 1,200 divided by 1.8. We root that, that's the velocity, and then you should get the maximum velocity of 25,82 meters per second. Simple. Very easy. So essentially, all you have to know is really this. The maximum conditions, you see centrifugal tension is a third of the initial tension. Right? Once that is done, they're requesting for us to find the power, and we know power is the initial tension on the right side, minus centrifugal tension, 1 minus 1 over E mu theta. So you guys can compute the power for me. And remember the angle of lap, what it says 1/2 of the circumference of the pulley. And of course, half, so a full circumference is 2 pi, a half will be pi, which is 180 degrees. All right. So it's a nice small example. Maybe I should just complete it and then give you one to do. Yeah. So this will be 3,600, which we found over here, minus our centrifugal tension, which was now a third of that, which is 1,200. 1 minus 1 over E. And of course, what's our coefficient of friction was 0.4. And we multiply by pi, right? Then we just times by the maximum velocity, and that's 25,82 meters per second. If you get this, you should get 44.3 kilowatts. So that's the maximum power this particular arrangement can actually achieve. So any questions with this? Fairly simple. So let me hit you with one more. Oh wow. It's a lot of information. Yeah. So, sir, in the example, the volume and the area are the same. It's not the same. Remember, when you're dealing with belts, we're working with kilogram per meter. So we're not working with the length here. So we just times it by the area. So if you do actually want to know the real mass, we have to find the length of the belt. And then, of course, we can actually find, but normally in belts, we just work per meter. Or for this kind of analysis. So we shouldn't worry too much about it. I just want to check if you're able to, okay, let's do one.
Sure.
Go for it.
Yeah, I just missed the angle theta.
Okay, so if you read the question, it says greatest permissible stress in, oh, sorry, it says with 1/2 of the circumference of the pulley. So that is 1/2 of the circumference. So what's a full circumference? 2 pi, and 1/2 is half of it, right? Which is pi. So it's 180 degrees. That's all. Nothing exciting. Now I want to give you guys a small tutorial quickly. It seems to be tight, but it's fine. No problem. Small tutorial, just a small test to see if you guys are able to do this. Okay. So I'll give you guys around 15 minutes to complete this one, right? Just move it over here. Okay, this is not with maximum power, but I wanted to give it to you after the other one anyway. But I realized that I'll probably have to continue on Monday again. Make the first session basically. So this is also in your notepad, obviously. And the mass of the one. Okay, cool. Yeah, so this is a very good question. I just want to see what's the same one. Yeah. So it's just 2,7 megapascals. That's just meganewtons per meter squared. I don't know, make it. And then, of course, this is just the rho is essentially 1,000 kilograms, kilogram per meter squared, per meter cube, sorry. And yeah, that's basically all. So what I want here is to find the maximum power. Oh, it is part of the maximum power. Strangely enough. Find the maximum power, which, yeah, it's weird. Okay, I think a question here is find the power, right? At normal conditions. And then find the maximum power. I don't know, it's quite weird. Find the maximum power. Okay. So I'll give you guys 15 minutes and then I'll step in on this. All right, students. Oh, Annalisa says she's a bandage on her head there. It cannot be that difficult. Let's have a look. So I see the power normal conditions first, right, and then maximum power. Okay, so remember, I just did this literally now. T1 is stress times area. So they're giving us the maximum amount of the allowable stress for the belt. That's 2.75 megapascals, right? That's a material limitation times the area, which is 0.125 times 6 millimeters. Now remember, this answers for the maximum power transmitted apparently. I'm just looking at that. I just gave you the normal condition as an extra. Maybe the question wasn't clear, right? I think what's next, I think the powers are the same. The powers are the same. Oh, but maybe, yeah, so it shouldn't be the same, yeah, but maybe it's a mistake on my end, yeah. So we can just call it the maximum power, right? Anyway, so TC will equal, oh, let me just get that answer first. 2.75 times 0.125 times. What's your tension? 2062.5 newtons. And then 2662.5 divided by 3. This is a practice problem, 6875.5 newtons. Do we need the velocity? So, although on the maximum power, okay, so we've got that. So the power is going to be T1 minus TC, 1 minus 1 over E mu theta times velocity. And so T1 was 2062.5. So much minus that, it's the same basically. And 1 minus E. So what is our mu? Our mu was 0.3. Angle of lap is 150 degrees, which you have to convert into radians. And that's 2,6179 times your velocity. So your velocity was given as pi times 500 revs per minute times 0.75 over 60. And then, oh, so is that what the maximum? See, this is what I was thinking. So this is your normal velocity here. I just want to make sure. So the minus term is, do you get the same value? 19.63 meters per second. And for your V max, remember you can take TC divided by M. Is that not so? Are we also there, students?
Yes, sir.
I'm here.
Yes,
Here,
sir.
but not.
Yes.
I'm here, but not.
Yeah, but we must we use the 19. I don't know for the correct answer.
The 19. Okay, that's fine. That's good. I'm just checking now. So you'll step back and do the analysis. So mass is density. So density is that's density there. It's 1 times oh no, whoa. What's this here? 1 megagram. Is that the mass? If the mass is 1 meter cube of leather is 1 megagram. What does it mean? I think what's supposed to happen there, I'm looking at it now actually. This is problem 2. So this is, well, the density is going to be, it's supposed to be 1,000. Oh, I see, it's 1,000. Don't know why it's so vague. It shouldn't be like that. 1,000 times 0.125 times 0.06, 0.006. And the mass should be, sorry students, it's the problem of the book, but yeah, it should be 0.75 and kilogram per meter. Yeah, sorry, it's worded very poorly. I should have put in the other one. Just forgive me for this. It's not difficult. It's just worded crap in this book. It's an old book. It is the volume, sir. Okay, yeah, no, this is so 687.5 over 0.75, and the maximum velocity is 30,276 meters per second. So there's Vmax. Of course, all you have to do is change the velocity over here. So for 19, you get 18.94, right? Is that correct? Is that correct, students?
Not exactly, but closer.
Okay, it's 18 point. What's it? You see, here's the actual problem in your notes. That's what it actually looks like. That's the same thing, but I think they made a mistake in that book there. I don't get that. That's the same. So let me just shift that on top here to avoid confusion. So let me just quickly verify what I'm saying here. 206.2.5 minus 687.5, 1 minus 1 over e to the power 0.3 times. What's that? 2.61799, close the bracket, times velocity 19.63. So yeah, so for this I get 14. Well, 14.68. So this is V mean, right? Operating one. And for V max, I get 30.276. Yeah, I find it quite strange. I'm not getting the right answers here. I get 22.649 kilowatts. So I'm not sure. Students, where did I make a mistake here? Can you guys pick
So I
up?
think it's to do with the centrifugal tension.
Tension.
I think
Okay.
so. Sir.
Yeah,
Because how I did it, so I took that for that TC. I'd said your mass times the velocity.
mass
Squared.
times velocity.
Squared.
Oh, you mean like this?
Yes, that's how I worked out my TC.
Oh, sorry. I picked up my mistake here because this is not. This is for maximum condition. Sorry, this is max. Yeah, sorry. That's max. So that's 0.75 times pi times pi. Oh, we have velocity already. Okay, I'll sort this out now. Okay, let's just do this right. So for normal conditions, our velocity was equal to 19.63, and then now we have to find the centrifugal tension, which was 0.75 times that velocity, right? Jason, what do we get for that one? So that's 289, right? 289 newtons. That is at normal conditions. So if you find your power there, in this case, it's going to be 206.2.5 minus 289 minus 1 minus all of that there, which is 0.3 times 2,61799 times that velocity of 19,63. Right? That's your mean power for normal conditions. So for max, it's no confusion, guys. For max, we have to do this over here. So it's TC equals T1 over 3. And of course, we got the previous thing of what is it? 687.5 newtons. So who got the normal power?
Sorry, sir.
Is that the, yeah, go for it.
So the first one that you did, isn't that max power? Because your answer you get there is 18.936, which is the answer that's.
Yeah, no,
okay.
it's yeah. Okay, I'm just gonna check now. Maybe you're right. Maybe it's the same. Let me have a look. Yeah. See the question is changing, man. It's the same question, but I'll show you now. So can you see in your notepad, it just says find this power which can be transmitted, man. You see here. But in the actual question I sent before, it says max power. You see there for the same answer. So this is not right. So let's see for max power. So of course you do that. The velocity you should get is now 30.276 meters per second. So now let's see if it's the same. Jason, maybe it's the same. 2062.5 minus 687.5. 1 minus exactly the same thing again. What's important just to understand what is maximum and what is not maximum. So if you can walk away with that, you've achieved, you've met the objectives of this particular section. Okay, guys, I think we're probably going to end off now. Probably have to continue belts next week for one session. I am seeing you for 3 sessions, so it's perfectly fine. See, the answers are the same. Yeah, I get 22. So that's maximum power. So are there any questions? So sorry, the question was worded badly. So for normal conditions, we have different speeds, remember? Remember the maximum power transfer occurs at a specific speed. So we have to find that speed. Are we all there? Is it more bandages on the heads? It's 5 minutes left. We're basically done here. And Elisa, you have a question? Mr. Mzam, Stuart?
Yeah, we're still good, sir. I think we need to go through it by ourselves, and then we'll see.
Yeah. Okay. So I just want to flash up something to you guys. So guys, thank you for attending today. I appreciate it. That you take an interest in your learning. Please check on Blackboard. I've posted a few notes. Extra notes to assist you with solved problems. Oh, just give me a second. I'll show you now. It's really not that difficult. And for the test, let's see the extra thing. For the test, you don't have to focus on. So I'm just showing the whole note here. It's from Theorem Machines. Right, maximum tension. A few examples here. Have a look. All the same. I've equipped you good enough. I think on what I'll do on Monday for the first session, I'll just conclude belt drives, but all it's basically remaining, students, is just V belt drives. So maybe I should just quickly share that with you and sneak it in here. Maybe I should just sneak it in to quickly show you. It's not going to take a long time, but I will go over it again. I'll probably order 2 examples. I think it's fair. But all it essentially does is that your equation for your the modeling of the tensions, you have now a groove angle. Of course, we're going to do this. I'm just giving this for information's sake. So if you can see the formula now, it's E mu cosec beta. So that's the groove angle, and normally we divide that angle by 2. So to give you the full angle, we have to subtract divided by 2. So I'm just letting you know that's all it's dividing essentially, and we use it both for V belts and ropes. Nevertheless, thank you for attending. Make sure you practice all the examples and practice problems. I've posted another note just to end that off, show you that as well. And this comes from the Mechanotechnics book in 5. I'll show it to you now. Of course, this goes without saying. Please go over it. And what's cool of this, it comes with solved examples. There's a few of them here. I show you if you can do all of this, you'll be more than sorted out. So yeah, you see there, it's got a few of them. Check out the cross belt one. It's nice. So anyway, okay, students, I'll see you on Monday. I'll see you Monday for strengths. Sorry, Monday for moms and then Tuesday for strengths. Yes, Brent.
Yeah, I just want to know what time is the test for next week Friday? Morning or afternoon?
1 o'clock again. 1 o'clock. Yeah.
Okay.
And then again, yes.
And just a quick update on the marks for the strengths and electives.
Yeah, I just told her I just saw some boy this morning, so I'll get that from her today. Like I said on the group.
So it's coming soon.
Yeah, so my plan is she'll give me the scripts. I think she inputted the marks already. But like I said, remember I need to first see what's happening before you know. So just give me time. But like I said, by next week, you might even get your marks Monday. Or maybe even Sunday. I'll give it Sunday off, Sunday morning. Depends. I'm just getting. But you will get it. Don't worry.
Okay,
I'm
thank
on
you,
this
sir.
now, so shouldn't stress too much. But Monday we're having a whole lecture on moms, right? And then Tuesday it's strengths. I think announcements came out already on Blackboard. I think it has. It will come out, but we can discuss further. But on Monday, I do want to do around maybe a hoist example, 2 hoist example in addition. Is that okay? But please remind me.
Yeah, that's fine.
Yeah. Guys, this is not difficult. Yeah, Matthew?
Is there test dates for the electros and the strength, or is that changed?
It's like I said to you, I'm just waiting on the okay from the HOD, and once she okays the plan, I will share it to you. But when I say don't worry, do not worry.
Okay.
The exams are shifted, so I managed to
Okay,
make a plan.
thank you.
Yeah, and I apologize for that you guys are feeling uncertain. It's a bit of a mess. It was also dropped on me last minute. But I will salvage it. Just give me time.
Sir.
Yeah.
So what happened to Miss Boy?